example, I'm going to create a universal connection as a ceiling to simulate a spring type connection between these two flanges. So at each of the 4 points that we have shown, I'm going to have a spring element type connection, representing a rivet or some kind of joint that's normal to these surfaces. So I've got two curved surfaces as flanges, and what we'll see in the end is a set of connections as spring elements, C-bush and RBE3 in the Nastran language, and then the spring elements will be spanned from one point on the top surface to a projected point on the bottom surface, and their orientations will be based upon a coordinate system that is created when we export the model for solution. So let's go get started with respect to defining our ceiling connection. Now, you would think that I'm creating a spring connection, so maybe I would want a bushing, but in fact, the ceiling connection comes from wanting to define connections as, in an automotive sense, for weather strips around windows and doors to create a seal, and those connections are typically represented with spring elements, and then they also need of that spring to be normal to the flanges, and those surfaces they change in direction. So this is exactly what we want, but maybe not for an automotive use case. So go ahead and into the dialog. First, start with the General tab, and then we notice that there's a orientation option. So if you leave this off, in our situation, we're going to select points, and then the software is just going to project that point down from its location onto both flanges if the point isn't on one of the surfaces. If you use orientation, then you will be able to specify the exact locations for your points on both flanges. So we're going to let the software figure that out, leave that turned off. And then I just pick my flanges here and there. Oops, not there. Second flange, pick the second body. I can also pick meshes and okay, so then we go into locations. And so for locations you have nodes, points, coordinates, and so on. So I'm gonna do this twice. First I'm gonna pick a series of points. And I'm gonna add these points just by selecting these 4. List, say OK. And then we have our tolerances. So the tolerances here, this first distance relates to your point locations or your definition locations relative to the element's center of gravity. So this is like setting up the distances for the spider elements that this point into the shell elements, and then second distance is the normal. So from the point, the distance to the surfaces. So distance to the top surface and distance to the bottom. In this case, this offset is actually 7 millimeters, so I need that to be greater than 7. Then we go into the physicals, and then here you'll see, it's not evident right away the stiffness directions, what they will be. Is probably an improvement that the software needs to show the stiffness directions of these connections. But the Y direction is going to be normal to these surfaces, and then these are in the plane normal to to the uniaxial direction of the spring that's going to be created. And then if we use this predefined option for the axis type, it tells you, the spring elements will be oriented based on a new coordinate system using a predefined method to define that coordinate system. And in this case, that predefined method is find the direction of your two-noded spring, and that becomes the y-axis of a new coordinate system. But again, we'll see that that's not going to be evident. So we have our ceiling connection now, and we see that it is not realized. But we have oops, and I messed up. So let me go and modify that, edit that, and what I wanted to do for the locations was I actually wanted to use this use original nodes location. And then what that is saying is for my points that I've selected, that's going to be the location for my spring elements. If I wanted to use some kind of discretization approach, I can do that, and I'll do that on a second example using the curve. So okay, so now if I update, you'll see these points 1, 2, and 3 will update to my actual selected points. So now I have a ceiling connection at point 1, 2, 3, and 4. Should end up with 4 spring elements and 8 spider elements. So now I'm going to generate the connection using C bushes and RBE 3s. So I say OK here. And then if I turn on my shell meshes as well, you can see that I've got spider elements from my projected point on the flange into this shell mesh, and same thing on the bottom. And then I a projected point on the second flange that defines the direction and the nodes for my spring elements. So I have a spring element with a length. It's not a coincident noded spring, and also we'll have a coordinate system at each of those springs when I go to solve this model, but right now not evident. Those coordinate systems aren't created until we actually write out an input file. If I look at these element associated data of the spring element mesh, I can list that out, and it says I have 4 elements in this mesh, and it's using a coordinate system for each one of these elements. It gives you the directions, the origin and the directions. So you can kind of see here that the z-axis of this coordinate system is parallel to the absolute z-axis, and then point in the plane is varying from one coordinate system at one element to the next coordinate system and the next element. Okay, so now just to verify that, I'm going to write out an input file. So I'm going to do File, Export, Simulation, and I'm going to call that this PDF file. So I go ahead and say OK to this. And so we see here I got 4 spring elements and 4 rectangular coordinate systems written out. I'm going to create a new new FEM and import that data back in. So I'll just say OK here, and maybe give it a name, import PDF. To associate that to a part, but I will do File, Append, that file to my empty model. Got the four spring elements and the four coordinate systems they're read in, and be able to rotate this around, and then you can see, yeah, the y-axis is the uniaxial direction of my springs. The x and z directions are normal to that uniaxial direction. So then that tells you, back in the original FEM, when I define this ceiling connections physical properties, the y-axis is going to be the uniaxial direction, and then would be my in-plane directions. Okay, so now I'm going to define those spring connections one more time. This time I'm going to do that using a curve. So if I say show and hide, I have some curves here. I want to use this curve as the definition source for my points on the. So I go ahead and define the ceiling again, and pick my flanges. Flange 1, 1, and flange 2, and then my locations. This time it's going to be a curve. And curve, so pick that, say OK. And then if I look at this, I can offset that curve in a vector direction. So if I don't want the points to be on that curve but offset in some way, I can offset. And I can discretize the line. In case I'm saying I'm going to start my points, 50 millimeters from the end, 50 millimeters from the start, and I'm going to have a step size of 50. So then my tolerances and physicals will be the same. So I could say OK here, and then OK, there's my first point. This is like 150 millimeters away, another 150 millimeters away, and then this is my end point. If I that, just maybe change the locations options to say maybe I want 25 for the start or the end, and then for the step size, I'll say OK. And then see this one, the start or the end kind of moved closer. It's like at 25 instead of 50. This one's still at 50 from the start, and then our step size got smaller. So that's pretty much it. Then same process. Go ahead and create these as springs and RBE3s if that's what you want, and go ahead and say OK. And then in the end, I have the same situation of uniaxial spring elements with local coordinate systems. The uniaxial direction is going to be the y direction. The in-plane perpendicular directions is x and z. Those springs are connected to the flanges with spider elements.